Hi everybody, welcome to another section in Calculus 3, section 16.3, double integrals in polar coordinates. So up to this point, what we have been doing is double integral. So pretty much this. Sorry, there's a typo, there's no equal sign here. Yeah, so integral of f of xy dA. dA can be written as dy dx or dx dy. We might have the limit as constant, in which case it is just a rectangular region. Or we might have something more general where it can be bound by two functions y equal 2 or bounded by two functions x equal 2. The outside always constant though. Right, so we'll evaluate the integral. Once again, sorry, there's no equal sign there. That is right. Now we do this the same thing. We still evaluate the same integral. That one, actually, the more general. We still evaluate the same thing, but this time we do in the polar coordinates. Certainly, there will be some advantage in polar coordinates. Depends on the limits or depends on the function. You'll see. Right. Now let's before we go there, let's just review. So the basic polar coordinates. You should have this in trigonometry with calculus and calculus 2. We have a point xy in rectangular coordinates. Instead of represent the point using xy, we can represent the point using r and theta. R is the distance from the point to the pole or the origin. And then with that, we have x values is equal to r cosine theta, y values r sine theta, and then Pythagorean theorem, r squared equals x squared plus y squared, and tangent of theta opposite over adjacent. Just one more thing though. When we use this formula to find theta, make sure theta is in the right quadrant. Is in the correct quadrant. Yeah, we need to check that. We'll see. Right, let's look at the first example. Convert the following points to polar coordinates. So originally we have x and y. We'll convert that into r and theta. So originally what we have here is x equal to 1, y equal to square root of 3. And we will convert this into xy into r and theta. Right. So simple enough. To find r squared equals x squared plus y squared. So that's what we have first. And x squared is 1 square plus square root of 3 square, which is 4. And to r squared is 4, so r is square root of that, which is 2. Right. So we have r. Next we will find theta. To find theta, the angle theta, we just take tangent inverse of y over x, but I'm just going to write tangent is y over x. And y is square root of 3, and x is 1. So theta is tangent inverse of square root of 3. Right. Make sure this is degree mode when we use inverse, so it's easy to tell what angle it is. So I have 60 degrees, which is pi over 3. Right. Now, That's good to know, but before we write the final answer, make sure that it is in the right quadrant. X is 1, y is square root of 3. Both of them are positive. So we have the point here in quadrant 1. And this one is in quadrant 1. So that's a check. So r is equal to 2. And theta is square root, pi over 3. So the point is r theta 2 pi over 3. Right, that's good. Try another one. On this one, we have x equal to negative 2 and y equal to 2. We will find the corresponding point in polar coordinates. So we just need to find r and theta. Same thing. R squared equal x squared plus y squared. X squared plus y squared. 4 and 4 is 8. So we take the square root of that. Square of 8 or square root of 4 times square root of 2 or just 2 square root of 2 for r. Right? Next, we find theta. Y is 2. X is negative 2. So we just need to find theta, which is tangent inverse of negative 1. So that's negative 45 degrees. Or pi over 4. Right. Before we answer, let's check real quick. Originally, the point negative 2 and 2. The answer must be in quadrant 2. But what point we actually have? Negative pi over 4. Negative pi over 4 is in quadrant 4. Right. So if we want to get into the correct quadrant, we need to go half a revolution away. So we're going to add pi to it to get to the correct quadrant. So we can just add pi to it, and that gives us 3 pi over 4. So the actual point will be r and theta, where r equal to 2 square root of 2, and the angle. Right. So, like I said, this is just a review of polar coordinates. Right. So from that, we convert into polar coordinates, meaning we find r and theta. Now we do the opposite to that, but for equation. Now, convert this following equation to rectangular coordinates. Rectangular coordinate meaning that we're going to have x and y in it. That's easy. For some of them. R equal to 3. So if we square both sides, that will be easy. And finally, x squared plus y squared is r squared. So we have x squared plus y squared equal to r squared. And that equal to 9. So this is the equation in rectangular coordinates. We just have x and y in it. Alright, that's the first one. Next, theta go to pi over 6. What we know is we can take tangent on both sides. So we'll take tangent on both sides. And tangent of pi over 6. Sorry, I forgot to use radian. Tangent of 30 degrees. Sorry. So actually that is 1 over square root of 3. Yeah. But tangent of theta is equal to y over x. So if y over x equal to 1 over square root of 3, and cross multiply we have x equal to square root of 3 times y. Right. Next, on this one, if we're going to square both sides, we have r squared equal to cosine squared. That's not particularly helpful. If it is tangent, yes, but if it is cosine, not so much. So what can we do though? So the point here is we're trying to get r squared, so that's still preferably if we can get to r squared, that is xy plus y squared. That's still our best option. So another way to get to r squared is either we square r or we multiply that by r. So multiply r on both sides. So we have r squared equal to 2r cosine theta. And next, r squared is x squared plus y squared. And r cosine is going to be x. And that is equation that have only x and y in it. X squared plus y squared equal to 2x. We can move everything on one side, complete and square. Will give us equation with a circle. But like I said, if we have x and y in it, that's good enough. Right. Next, r and secant. Right. R of secant is 1 over sine, so we have 5 over sine theta. We can write this like over 1 cross multiply r sine theta equal to 5, and r sine theta is y equal to 5. Right, so it's not that bad. So as long as we can write this equation x and y, that should be good. Alright, but that's just a review in polar coordinates. Now we actually go to the calculus part. So, double integrals over polar rectangular regions. So why do we call this one in polar rectangular regions? Remember, when we talk about rectangular, meaning that the limits is going to be constant. So in here, as you can see, limit for r constant, for theta constant. Same thing, r and theta, r and theta. So, I mean, if we're going to say this is the axis theta, this is r, axis r, theta bounded by 2 constant, and r bounded by 2 constant. Let's say theta is from alpha to beta, and r bounded from a to b. In that case, we have the rectangular region. But this is rectangular in r and theta, not in x and y. So that's why they said it says polar rectangular regions. Bottom line is we have the constant limit for r and the constant limits for theta. Okay. Now, once again, we have the same thing, but this time we have the function in terms of r and theta. So double integral, if the function in r and theta, dA is equal to the integral of this. Of course, this should be alpha. Actually, I changed the note online, so there should be alpha here. So theta is between alpha and beta. Theta is on the outside, so the limit is from alpha to beta. That's good. R is between A and B. Between A and B, we have dr. So the double integral of the function in polar coordinates of r and theta, dA, is that. Now, what's different here is this r. So when there's r there, what we have is the dA is equivalent to that. So the note that I'm trying to write here is dA. For previous section, we can say dA is equal to dx times dy or dy times dx. Either way, let's say the x is the unit of length, for example meters, right? So let's say x is meter, y is also meter, so same thing here, and meter times meter, so for dA it is meter square. That sounds right, about right, because dA is like the area, so meter square, perfectly fine there. Now suppose we write r dr d theta. The question is why r has to be there. Actually, when we go to section 16.7, we'll see why this r has to be here. But r is the radius, or the r is still distance, so the unit is m, is meter, which is good. Theta, angle has no unit. So if we don't have r here, the unit for that is just m, which is wrong. What instead we have is r, which is unit is also m times m is meter square. So that, meter times meter is meter square. So we need r there for the unit to work. Or we can look in this, what we look for the dA is a small segment here. And we have the change in angle times the radius. So if we talk about the arc length here, it's going to be r times dr. That times d theta. Sorry, that gives us the arc length. And then this side is the dr. So at dr or d theta will give us the area of that portion, which is equivalent to dA. Right, like I said, when we go to section 16.7, this will explain a lot better. But for now, we say dA in polar coordinates is r dr d theta, and don't forget there is the r there. Right, let's just look at the first example. I'll find the volume of the solid bounded by the paraboloid and the xy plane. So pretty much we find the volume below the function. Right, 9 minus x squared minus y squared. The graph of that is the paraboloid. So we have the paraboloid like that, and we find the volume below that, but above the xy plane. Right. Now, on the xy plane, when z equal to 0, so this is at z equal to 0, because that on the xy plane, when z equal to 0, what we have is 0 equal to 9 minus x squared minus y squared. So meaning that we have x squared plus y squared is equal to 9. So that is a circle, right? Circle of radius 3. And it is bounded inside this, so we talk about this region. Right, so it's good, right? Now, first of all, let's just write this out in rectangular coordinates. So we're trying to find volume, right? So the volume below a surface is given by this volume equal to the double integral. We have the volume below the surface function, so we're just going to say 9 minus x squared minus y squared and dA. Right, and over the region R on xy plane, we just say the disk, but kind of difficult to write the limit for that disk, right? So instead of writing that, we just write say 3 for the radius, like that. This is where we say a picture was 1,000 words. So it's just a disk. That is if we write this in rectangular coordinate. Now if we switch this into polar, now in polar, what do we have? In polar coordinates, x equal to r cosine theta, right? And y equal to r sine theta. We're going to use that certainly. And then the region R, which is that disk, right? Which means this is a disk radius 3, so we say R between 0 and 3, and this is one complete revolution, so theta from 0 and 2 pi. Right, so yeah, so now if we write the limit in terms of R and theta, that's what we have. Now write this in polar coordinate, we will have 9 minus x squared. X, we're going to use r cosine theta. So we need to write the function in terms of r and theta. That should be minus, right? Right, so we have the function now in terms of r and theta, which is good. Now the dA here is r dr d theta, right? So now the dA is r dr d theta. So the function in terms of r and theta, and then r dr d theta. So what are the limits? Easy enough, right? R, the limit, the radius will go from 0 to 3. And the inner radius, the inner limit, the outer limit is theta, which go from 0 to 2 pi. Right, try to simplify this. Right, try to write small. 9, that will give us 9 minus r squared cosine squared minus r squared sine squared r dr d theta. So we have 9, and both of them have r squared. I factored out. Then we have cosine square plus sine square, and then r dr d theta. Cosine square plus sine square is 1. So bottom line is this becomes 0 to 2 pi, 0 to 3, and then 9 minus r squared. That's nice, right? And then we still have r dr d theta. Now, what can we do here? Of course, here we can integrate double integral. Should be easy. Can be even easier if we use the Fubini theorem. Notice that the function here only depends on r. Or we say the function is separable. So we group all the r together and all the theta together. Right? All the r together. This is the limit for r, the function, and then r. So pretty much all of this in terms of r. So put that into one big integral. 9 minus r squared r dr. What's left is theta. Yeah, we can do that because the limits are constant and the function here are separable, the function of theta and the function of r. We cannot do this if we have r plus theta in the middle. That's not separable, but this one is. Right. I'm just going to put that in the calculator because I'm running out of space. Integral from 0 to 3. And we have 9 minus, I'm just going to use x instead of r times x dx. And that gives us 81 over 4. Yeah. This integral will be easy. That is just theta or from 0 to 2 pi. So put in 2 pi we have 2 pi. Put in 0 we have 0. So 2 pi minus 0. Bottom line is we have 81 over 4 times 2 pi. So 2 and 4 cancel out. We have 81 pi over 2. So it's not that bad because in polar coordinate this is a separable function. That is not a separable function in terms of xy, so that is bad from the beginning. And not only that, parameterize, write the limit for the circle. That will be a lot more difficult than the limit in terms of polar. Right? Right. So that's what we have. Let's look at the next example. I'll find the volume beneath the surface, below the surface, and above the annular region, which is an annulus is the region between two concentric circles. So a donut, pretty much. So this is what we have is the donut radius, inner radius 2 and outer radius 4. So we're going to have 2 on the inside and then 4 on the outside. Of course I can draw better than this, but good enough. Right, and we'll talk about this. That is R. And of course we have the limits already, which is good. Now find the volume. First of all, if we write the volume, we're going to use the function xy plus 10 dA. Right, I can write R here, or even better, more descriptive, I'm going to draw the donut. That better. Right. So in polar coordinate we have x equal to r cosine theta once again. X equal to r cosine theta and y equal to r sine theta. We already have the region R, so which is good. We're not going to mess with that. Right. Now let's write the limit. X is r cosine theta and y r sine theta plus 10. So x times y plus 10. Most importantly, that note dA is r dr d theta. Don't forget there's an r there. Limit for r easy, 2 to 4. Yeah, I can say r equal to 2 to r equal to 4, but 2 to 4 is good enough. For theta, 0 to 2 pi. Right. Bad news is this one is not separable. We cannot do that. Right. So try to write small because we might need a lot of space. Right, that gives us r squared, and then cosine times sine, or sine times cosine, plus 10, and then r dr d theta. We can multiply the r inside if we want to, but now sine cosine, what can we do with sine cosine? So there are a lot of ways to do with sine cosine. We can use substitution, or we use this. If we have cosine square, we can use power reducing, and we will have 1 plus cosine of 2 theta over 2. So that is power reducing. Sine square, also power reducing. I should still cosine though. Cosine of 2 theta. Over 2. And if we have sine and cosine, well, what's that? Remember, the double angle sine of 2 theta is equal to 2 sine cosine, right? I just need to divide by 2, and I will have sine of 2 theta over 2. Yeah. So whether we have double a square or the product of sine cosine, we can use this to simplify, and we can integrate after that. Right. So we have r squared still. Sine and cosine will be equal to sine of 2 theta over 2. Still plus 10 dr d theta. I will multiply the r inside. That gives us r cubed. Let's write the 1/2 in front. That look better. So 1/2 r times inside will be r cubed sine of 2 theta, and then plus 10r. This one is not separable, so we just have to integrate. So multiply the r inside, we have r dr d theta. Now let's integrate with respect to r. Integral with respect to r, we have 1/2 r cubed integral of that is r to the 4th over 4 sine of 2 theta plus 10 integral of r is r squared over 2. We have to evaluate from 2 to 4, and when we've done that, we just need to evaluate integral with respect to theta. Right. Let's simplify this just one bit. 0 to 2 pi. Right. R to the 4th, so that is 8. So I have r to the 4 over 8 sine 2 theta. 10 and 2 cancel, that is 5. Now I'm going to put 4, I'm going to put 2 in it. So first, we're going to put 4 in. We have 4 to the 4th power over 8 sine of 2 theta plus 5 r square, which is 4 square. Sorry, yeah, and then subtract. Now we're going to put 2 in for it. 2 to the 4th over 4 sine of 2 theta plus 5 times 2 square. Right, so that is inside d theta. Right. 4 to the 4th is 256, I believe. Yep, divided by 8. 32. So we have 32 of them. And 2 to the 4 is 16 minus 4. So we have 32. Let us say it. We have 4 to the 4th divided by 8. And then we subtract 2 to the 4th over 4. So that should be 28. I mean, should be 28. So we have 28 sine of 2 theta. And then 5 times 4 square minus 5 times 2 square. $60. Right, so this will be simple enough, right? So integral of 20 sine 2 theta is negative cosine 2 theta over 2. And 60 theta, so that's just 60 theta. Now I'm going from 0 to 2 pi. Or negative 28 over 2, that's 14. So now we put in 2 pi, we have negative 14 cosine of 2 times 2 pi plus 60 times 2 pi. So that is where we put in 2 pi. Yeah, negative 14, 2 times 2 pi, and then 60 times 2 pi. And then subtract negative 14. Put here cosine. We put 0 in for it now. And then 60 times 0. Right, cosine 2 pi, cosine 4 pi. Cosine 4 pi is just like cosine 0, which is 1. So this is also 1. So we have negative 14 and then negative. So that plus 14, so that's 0, and then we have 120 pi. Right, let's check real quick. First I will change to the radian mode first. And I evaluate the integral math number 9 from 0 to 2 pi. Because you can enter any of this if you want to. I will just enter this 28 sine of 2 theta plus 60 that's 120 pi, so that divided by 120. Yes, that is pi. So yeah, so the answer is correct. So 120 pi. So it's not that bad. And those will come in handy if we have cosine square, sine square, or sine times cosine. Right, so that's what we have. Right. More sample. Now we have this one. This is sample. Sketch the region, evaluate the integral over R using polar coordinates. So we're going to use polar coordinates. First R, the radius between 1 and 2. But the angle though, only from 0 to pi. So we talk about quadrant 1 and quadrant 2. So radius 1 and 2. And then angle from 0 to pi. So we're talking about between radius 1 and 2. So we're talking about half a donut. Right, so that's easy. We have the limits. So that should not be any problem. Now we just need to rewrite the function. Right, let that integral be I. So in polar coordinate, x squared plus y squared is r squared. We could substitute back like we did here. X is r cosine, y is r sine, and then simplify. But in polar coordinate, we have x squared plus y squared. Just make that equal to r squared. No need to do substitution for r cosine, r sine. We just say it in polar coordinate. X equal to r cosine, y equal to r sine. But x squared plus y squared is r squared. So r squared for x squared plus y squared. So that's actually kind of bad if we have to integrate like this, if we just have dr d theta. But remember, in dA, it's going to be r dr d theta. Right. Now the limits for r inner limit between 1 and 2. Outside limit between 0 and pi. So good thing is, this one is once again, we have constant limits, right? 0, pi, 1, 2. And the function here only depends on r. So this is a separable function. So it's now just group everything with r together. So those that related to r. So pull that out. Then we have 0 to pi of d theta. And then what's left is 0 to pi d theta. Yeah, the answer is not ideal because that looked like with the ln of something. Right, let's try it. Let's go from 1 to 2. And we have 1 plus x squared, and we have x. Let's say times x dx. That doesn't help. Right, would mean we actually have to do it. Right, so it's not that bad. It's just substitution. Without the r here, that is trig substitution. We have to use the tangent and then all kind of that. But now substitution. So for substitution, we're going to let r square, or just 1 plus r square be u. So let u equal to 1 plus r square. We can take the derivative. It's 2r and multiply and then divide. We solve for dr, and dr will be equal to du over 2r. I'm going to substitute in for dr, and that is u. So the integral, let's change the limit also. Originally r go from 1 to 2, but u is 1 plus r square, so 1 plus 1 square is 2, and 1 plus 2 square is 5. So the integral will go from 2 to 5 in terms of u. One plus r square is u. R dr du over 2r. Yeah, so that is the substitution. The r cancel out. The 2, take it outside. And then the integral from 0 to pi, that's easy. That's just pi, right? So pi minus 0, but just pi. Right. The integral 1 over u. By the way, let's just rewrite this before we integrate. It's almost there. 2 to 5. Those are limits for u. And then we have 2. Take it outside. That becomes 1/2. Then we just have 1 over u du. Put in pi, put in 0, so we just have pi minus 0. Integral of 1 over u is ln of absolute value of u, where u go to 2 to 5. And if you say where's the 1/2, of course the 1/2 still there. And then pi. So we put in 5, we have 1/2 ln of 5 minus 1/2 ln of 2 times pi. So is that what we have? 1/2 0.5 ln of 2, ln of 5 minus 1/2 ln of 2. Yeah, so that's the answer. If we want to, we can factor 1/2, and we have ln of 5 minus ln of 2 pi. And when we subtract the ln, that means we divide them. So we have 1/2 ln of 5 over 2 pi, or 1/2 pi ln of 5 over 2. We can confirm that 0.5, that's 1/2 ln of 5 over 2. Yeah, still the same thing. So it's good. That's our answer. So it's not that bad, right? So usually when the region is something that is nice in polar, yeah, so it's easy to convert everything to polar. Right, let's go to something more complicated. We still have the integral, but this time what we have is, again, dA is r dr d theta, but the limit here is the dr is inside, so we have the limit for r equal to meaning that there are two functions of theta. The outside though still have to be constant. Double, triple integral doesn't matter. The outside integral must be, the limit must be constant. But inside we might have something complicated. Let's see how it works. Right. Let's try to write this for the region outside of the circle r equal to 2 and inside of this circle. So we're talking about this. Of course, that. Right. First of all, we have to find where's the intersection. Where are those points? So first find the intersection. Both of them equal to r, so why don't we let them equal each other? And then just solve for cosine of theta equal to 2 over 4, which is 1/2. So theta equal to cosine inverse of 1/2, or theta equal to opposite to that. Because in a unit circle, these 2 points have the same x values, therefore the same cosine values. So cosine inverse of 1/2 should be pi over 3. Yeah, so pi over 3. And this is negative pi over 3. So those are the limits. Right. Now we will set up the integral. We will have the function and once again I prefer drawing. If you don't want to set up the limit in terms of x and y, just draw the graph. Always use r. Right. Now, we do know that it's going to be dA is r dr d theta. That's for sure. I said that many times and I still forgot. Remember, always dA is r dr d theta. Now, what will be the limit for r? So remember, let me find this real quick. On 16.2, whenever we set up dy dx or dx dy, if it's dy, we look along the y-axis. If it's dx, we look along the x-axis. Same thing here. If it is dr in the inside, we look along the r, meaning from inside, we look from here on out. So here onward. That is look in the r direction. Notice that when we look in that case, what we see is the first function is this, the function on the left, and then the function on the right. So from inside, the first thing we see is from the circle r equal to 2. So from r equal to 2. And after that we see that come from r equal to 4 cosine theta. Right? we see this one first, and that's one after that. And then d theta negative pi over 3 to pi over 3 for theta. Right, so just that. I'm not going to evaluate that. There's plenty of, there are a few more samples to evaluate this, but yeah, let's just integrate. We cannot integrate, by the way, because we don't have the function. Right, so we're good. Next, convert the following integral to polar coordinate, then evaluate. There's a typo here. Sorry, that should have been that. We know x, that means the outside integral have to have x in it, so this is why this is dy dx. Right, let's just evaluate. What is square root of 9 minus x squared? And what is negative square root of 9 minus x squared? So let's consider that quickly. Here we have y equal to potentially plus or minus square root of 9 minus x squared. Right, could be positive or negative. Let's square both sides. So that gives us y squared equal to 9 minus x squared. Move the x squared over, we have x squared plus y squared equal to 9, which is the circle center 0, 0, and radius 3. Right. So now let's just sketch. And we have a circle of radius 3. Just draw a very small circle. If you're going to do like I do, just hold the pen very steady. Rotate the paper. Never rotate the hand. Just rotate the paper. Hold this very steady. Right, so we have a circle. Alright, the one above is y equal to positive 9 minus x squared. The one below y equal to negative square of 9 minus x squared. Right. So the positive one is above, the negative below. Right. So that is the limit of y. Now, but more importantly, the x here though, from 0 to 3. So we only talk about the right half of the disk. So that is the region R. Right. Now if we want to write this again, we can just say it. Let's integrate this on the right half of the circle of the disk radius 3, and then just write dA, because we're not going to use dx dy or dy dx. We're going to use r and theta. Right. For that right half of the disk, we can say the radius is from 0 to 3, and the theta angle will be from negative pi over 2 to pi over 2. That will be the limit for R. Now I'm going to write this in polar coordinate. So in polar coordinate, first x polar coordinate is r cosine theta. Right. dA always r dr d theta. That is dA. The limit for r, the inside limit is for r, that go from 0 to 3. and theta negative pi over 2, pi over 2. So luckily this one, the function is separable. By the way, we have r and r. Let's multiply them together. And then just group everything with the r in it. So concluding this have r in it, and then certainly r squared and dr. So from 0 to 3, we have r squared and dr. What's left is d theta for theta. Right. By the way, we have one example like this where we have the limits are symmetric. If the function is odd, the integral is 0. If the function is even, it's just going to double from 0 to pi over 2. So that's not a very effective properties. If it is odd function, it will be a lot better, but it's not. But what it is, so let's just evaluate, keep this in radian mode. We go from negative pi over 2 to pi over 2, and cosine of theta. So that's 2. And what is the other integral? That goes from 0 to 3 of r squared. So it's 9. So this is pretty much 9 times 2. So it's 18. Right. The next one is extremely interesting. It's the classic problem. The solution kind of unique. First one, yeah, that's no typo. It's just dx there. And then you say, that's just a single integral, right? What's wrong with that? Why do we need? Why do I put that example in this section? Right. Now, as a reminder, previous section I did say that there's some certain function that we cannot integrate. And that including is like something like this. Nobody can integrate that. Or we have e to the x square dx. We cannot integrate that either. Especially that when there's no limit, we cannot integrate. Of course, if there's no limit, we cannot estimate. We can use power series, yes, but we're not going to do power series here. So there must be a way to do this. Actually, I said the solution is kind of very interesting, so that's why I put this here. If you go to a little higher level of vector calculus or multivariable calculus, definitely you will see this example again. Or you go to statistic, you see this again, because why does that have to do with statistic? Let's just graph this function, see what happened. We have e to the negative x squared, right? Where's the x? Right? Don't see yet, but let me zoom in. I will zoom in again. So what we have is the bell curve. So very popular in statistics. Right, so first I'm going to let I equal to this. But if we have x, we can also say, yeah, if instead of x squared, same thing. If I'm going to use y, right? Now the genius here is we're gonna multiply those two together. So that integral square. First we're gonna have the integral from 0 to x. I mean from 0 to infinity. And then we have the integral from 0 to infinity. Now, the Fubini theorem, in this case, actually we group together. So we have I squared equal to double integral 0 to infinity, 0 to infinity, e to negative x squared, e to negative y squared. Dy dx or dx dy, doesn't matter. Right. So at this point I'm overlooking the improper integral. Just focus on the integral, the mechanics of it, the proper integral, the notation with the infinity. We'll worry about that in a minute. Right, next, let's simplify this function. One more step. When we multiply, we're going to add them, right? So we just have this. And then we can just put x squared plus y squared, which of course dy equal to r squared. However, if we have r squared, we still cannot do it. However, as you see, x squared plus y squared look like if we're going to have r squared, that could be nice, very nice, right? Now, the best part of this is this logic. We talk about the limit. X can go anywhere from 0 to infinity, y can go anywhere from infinity. So we're talking about the whole region here, the whole first quadrant. But now think about that. That is the whole first quadrant. But can we say the whole first quadrant in this case? Meaning that if we let r go from 0 to infinity and we let the angle be anywhere from 0 to pi, 0 to pi over 2, we certainly will cover the same quadrant. Right? This will not work if this does not go to infinity. Because this go to infinity, we say we can use the square or a quarter of a circle. If we extend that to infinity, those two areas will be the same. That's the idea of this problem. So for this region, r between 0 to infinity and theta 0 to pi over 2. So that will be the limit. And now we will change the problem. So I squared. Like I said, I will overlook the infinity for a moment. Sorry. Now first, I'm going to write this in polar. So two polar coordinates. Negative x squared plus y squared, that definitely is r squared. And as always, dy dx or dA is r dr d theta. Now with this r, the substitution is conveniently done. Right, r limit from 0 to infinity and theta 0 to pi over 2. Right. Also for Fubini theorem, there's a bunch of r here and theta. So if we group the theta, we have 0 to pi over 2 d theta. And we group everything with r. E to negative r square r dr. Right. The first one is easy. For the second one, I'm going to use substitution. Like I said, there's a whole thing about improper integral too. So let's just do that properly, since we have enough space. The first integral, just 0 from 0 to pi over 2. Theta from 0 to pi over 2. Now, improper integral. For infinity, I'm going to say let c goes to infinity. So this integral will go from 0 to c. And then we have e to negative r square r dr. Yeah. So that's the proper way to handle improper integral. Now, the nice thing about this is if we let u equal to this, there's an r for the substitution. So that's exactly what we do. So let u be negative r square. We take the derivative. Multiply dr and divide by negative 2r. So du over negative 2r is equal to dr. So that's good. Now in terms of the limits, we go from 0 to c for r. R go from 0 to c. And u is equal to negative r squared. So this will go from negative 0 square and negative c square. Right. So use that substitution. Continue the integral. We have put pi over 2 here. And then subtract where we put in 0. Still have limit as c go to infinity. The limit now will change from 0 to negative c square. E to the u or dr is du over 2r negative 2r. Cancel. And pi over 2. And then limit. That is negative 1/2 e to the u du. So the integral is easy to do, right? So pi over 2. Limit c goes to infinity. The integral of e to the u is still e to the u. That goes from 0 to negative c square. I'm going to put negative c squared for u and put 0 for u. Right. Now, e to negative c squared, c go to infinity. So what happens if we have e to something that goes to negative infinity? Exponential function, if it go like this, when it go to negative infinity, that one go to 0. Yeah, this is exponential function. when I go to negative infinity, it go to 0. This one go to 0. E to 0 power is 1. So negative 1/2. So we will have pi over 2 times 1/2, which is pi over 4. And finally, that is I squared. So finally, I equal to the integral from 0 to infinity e to negative x squared dx is equal to square root of pi over 4. Because what we calculate was I squared. Now we have to take the square root back, and that gives us square root of pi over 2. Now, another thing about this is, you saw the graph, right? It's bell curve. The right half is square pi over 2. The left half is also square pi over 2. So if we want the area of the whole thing, will be square root of pi, because this is symmetric. Let's look at the graph of e to negative x squared. It's the bell curve, right? Because that is an even function. Right. I did say that this problem is interesting. I said every little detail we already know. But the genius here is that we consider one of them is I, the other one is also I, multiplied together. We make things a lot more complicated. But at that process, when it goes to infinity, we turn the square into a quarter of a circle. And then think about this. The idea is, if we have a square that is extended indefinitely, that will cover the whole plane, right? Now, same thing. If we have a quarter of a circle where the radius extended indefinitely, once again, that will also occupy the whole space. The same space, if you will. So this only works if it goes to infinity. If it goes to something else, we cannot do that. Because if it stops at finite, we will have the square. We don't have the infinite area in the first quadrant. So, and to evaluate it, it's not that bad. Might have to use improper integral, but bottom line is it turned out to be very nice. Yeah. So all of the math you already know. I mean, you know the math, how to do those problems. But the idea here is very, very interesting, including two things. Yeah, to get to I square and to take care of those area, those limit. Those are two very nice ideas. Right. Now, the area in polar regions. Right. I think this is a very bad example to put here. So, the area is equal to the integral. Bottom line is, if we just want the area, we're just going to put 1 here for the area. Yeah, so this 1 for the volume. I want the volume, which is not what we asked to find here. So, yeah, so that's not the point of the problem. So I'm going to do that last because this is not related to this integral. But notice that the one important thing is when we find the area, make sure that the limit here have to be within one revolution, one cycle. Yeah, we cannot just find the area of this circle where we say the area, the angle go around 10 times. We cannot do that. So the area have to be whatever the limits are, have to be within one revolution. The radius though doesn't matter. Right, I said we might go back to this, but let's just focus on the one that actually calculate the area. Right, so let's take a look at this second example. Right. So we want to find the area here. So first what I'm trying to see is what will be the endpoint here, so we can find the intersection. One of them is r equals square root of 2. The other one is r square equal to that. So if I take the square root, r equal to 2 square root of cosine 2 theta. It's kind of difficult to solve like this, so let's square both sides. So cosine of 2 theta equal to 2 over 4 or 1/2. And we did mention about this, which is 1/2. So we can solve for theta easily. So 2 theta is cosine inverse of 1/2, or 2 theta equal to negative cosine inverse of 1/2. So what is cosine inverse of 1/2? That should be 60 degrees. Yeah, 60 degrees of pi over 6. Negative pi over 6. And divide everything by 2. So theta is pi over, 60 degrees is pi over 3. And divide by 2, we have pi over 6. Negative pi over 6. So that will be between pi over 6, negative pi over 6 to pi over 6, negative pi over 6 to pi over 6. So we look at that angle here. So the region is between those limit. So this region R, we can say theta is between negative pi over 6 and pi over 6. And then R, right? Now we look for R from the inside out. What do we see first? First we see is this one, right? Which is from the circle, square root of 2. And we see on the outside is from whatever that is. I don't know how to even pronounce that, but it's not important. Notice that this is r squared, so we need to take the square root. Yeah. So that is the region R. If we just want the area, we will put nothing here. And we're going to have we're going to calculate that area. Right, limits. The constant limit have to be on the outside. And the inner limit can be between two functions. So no Fubini theorems here because the constant limit are not constant. Cosine 2 theta. dA, R, dr, d theta. So have negative pi over 6 to pi over 6. R, limit r squared over 2, integral. Go from square root of 2 to 2 square root of cosine 2 theta, d theta. So we have 1/2 r squared. I'm going to put this in first for r. and then subtract, put square root of 2 in there. Right, now pi over 6 to pi over 6. We have 1/2. 2 square is 4. Square root, square cancel the square root. Minus 1/2 times 2 d theta. I run out of space, but so I'm going to just stop at this. I'll say this is 2 cosine of 2 theta. 2 and 2 cancel out, minus 1 d theta. I know this one is not going to be nice and even, so run out of space, but that's the idea. The integral here is very easy to do, so I'm not going to bother to do that. Once again, if we want the area, we're just going to have 1 here, and the area equal to that. It could be in rectangular, in that case dy or dx, or if it is in polar, or dr d theta. Right. So since this is the only problem that has the problem with the area, and the previous problem is not, so I'm just going to omit example 1, and I'm going to stop the section 16.3 here. As always, thank you for watching.